Okay, so last time what we were looking at was delta network, and I had not given the formal definition so far. But we actually, I was trying to give the fundamental reasoning why a delta network is going to be a delta network, and I told you that when I am actually connecting the inputs or the outputs from the previous stage, and since the output this is being selected based on a certain digit in the address. Okay. So, if I am going to select all the inputs, if any one input is being selected from say some value x, and if I choose from some other value y, now then there is going to be a problem actually, because this onward path will be decided by a different set of digits. So, same digit cannot be used to reach to the same output actually, same combination of digits, that is not possible. So, all the inputs, this is x, then this also has to be x, and wherever you are connecting this also has to be x, this also has to be x, that is the condition which need to be satisfied. So, if you can build up a Banyan network with this condition, you will get a digit controlled routing network actually, or delta network. So, for that 8 by 8 case, I think that is what we were discussing last time. So, I had drawn something, but something like this. So, now this is 0, this is 1. So, I can actually connect in any way I want. I need to build up only a multiplexer tree, that is very important. I should not be able to isolate, I should not end up with a situation where from an input you are not able to reach to all the outputs, that condition should never happen. So, there has to be a demultiplexer tree. So, with 0 for example, I can connect here, 1 I can connect here, I can do whatever way I want actually. So, I am just connecting something arbitrary actually, and from here there are again 2 things, these are again 2, I can connect in any fashion I wish. Something like this. So, I am just making an arbitrary demultiplexer tree and based on the delta network. So, next one which I will take, this will also have now 2 outputs. Okay. I can actually use these or I can use this system material for me. As far as I am going to share a multiplexer tree, it is fine. Okay. So, for example, I can actually choose, when I am connecting here, it is connected to 0. So, this one cannot come here, remember, because then it is not going to be delta network. Okay. So, I have to connect only a 0 here and a 1 here. So, this leaves to me only one choice, but maybe I can actually connect, this is 0. So, I connect this thing here and I am able to cover up these 3. So, part of the multiplexer tree from here is this to these 2 I have not covered actually so far. So, for covering these 2, I have to choose from these actually, from any one of these 2, or I can choose this one. So, if I choose this, these are like 4 by 4, this will be another 4 by 4 and then mapping. So, I can do it another way around also. So, for example, if I choose this one, so this one cannot be connected to these 2, because then I will not be able to form a demultiplexer tree. I have to connect this mandatory to only these 2 conditions, these 2, no other option. So, there is a 0 and there is a 1. So, this one is connected to 1. So, this one has to go to here if it has to be delta network. I am just creating a random topology, I have not pre-planned it, I am just doing it here in the class just to show as an example how does it work. Okay. So, the next one is this, because this 2 has been already covered for this and this was not there. This is also 0, so this will also be 0. You can check actually, if I put certain number, the 0 from here, 0 here and a 0 here, If all 3 digits are 0, I will always end up with that box. Okay, in any one of these 4 inputs, all 3 zeros will always give, I will come to this output. That is the only map which is possible. If I put 0 0 1, I will take 0 here, 0, and this will be 0 0 1. So, I am actually assuming there are 3 bits. B2 will be used for routing here, B1 will be here, and B0 will be here. Okay. I can now expand for the other one. So, there is a 0 and there is a 1, I have to build up a demultiplexer tree. I can choose this one. Now, remember this is taking input from 1. So, if I choose this one option for a demultiplexer tree, I am covering these 2, and this guy or this guy has to be chosen, this cannot be chosen in that case. So, but of course, later on you can find out, you can do shuffling of these things, move here and there, twist around, and you will be able to build up some nice topology. So far it looks very bad. So, if I connect, this is 1, so I can only connect 1 here, that is a condition for delta network. This 0, because I have connected here, which is connecting these 2, so I have to either use this or this is already occupied. So, I can only use this option. So, I will take this and this will take 0. Okay.
For the one, sir, for the connector we had to use the middle
this one.
Yes, for connecting one.
This is 1 and this is 1.
Yes. My doubt is that for one week, could we have done that switch? We have connected 0 with
The bottom one.
Yes.
Can I connect this 0 here?
No, sir. My doubt is, can I connect one, not connecting in that one, sir? Yes. Down.
This one.
Could we have connected here?
Here.
Yes, sir.
Now, how? Because one can only be fed here and one can only be fed here. The 2 zeros have been taken, 2 zeros has to come here. If you do this, you won't get a 0 1. See, you have to understand the balance. Because this is a binary output, so half of the nodes will take the inputs from all zeros, half of them will take from all ones. So, you have no choice actually in that. But you can make arbitrary lot of combinations, each one will give a different permutation. Different permutation will be a set of permutations which will be permitted. Okay. So, now take from here. So, this is 0, this is 1. So, this 0 has to go obviously here, there is no other option. You cannot connect a 1 here, and this 1 will be taken by this guy. So, where this has to go? There are only this and this which are available. This is taking 1, this is taking 0. So, this 0 has to go here and this one has to go here. This is another example actually now. You put a 0 0 0 here, where you will go? Go to top comes here, put 0 0 here, top, again you will come here. Only thing, the numbering is not 0, 1, 2, 3, it is not like that, but numbering is fixed. So, the moment you give address as 0 0 0, it will always come at this output. Okay. And of course, if there is a packet going for 0 0 0 direction, this switch, this line and this line will be busy. There will be some other pattern which may not be permitted, only certain set of patterns will be permitted, and that is a specific permutation which is allowed. Okay. So, this is another delta network of 8 by 8, but usually we can keep life simple, this has been too complicated. So, best way is to go for that inverse Bain configuration. or then we will actually now talk about another things which is known as shuffle net. Because usually what happens is whenever you are going to fabricate this stuff, each one is in a VLSI or in optics, this is nothing but a small processor in itself, is buffer and everything, and I have to interconnect. So, if it is an optical thing, and for example, lot of buffers, a lot of these processors have been built, I stack one on top of other, these stages, I have to make an interconnection between them. So, this interconnection has to be something which is uniform and I can repeat it. This interconnection is different, this interconnection is different. So, actually it is not desirable for neither for VLSI nor for optical computing implementation. So, both ways this will not be suitable actually.
We can take any number of delta networks like
Yes.
where in the previous delta network you said that we can't establish one two connections simultaneously.
Here also, here you might actually, I do not know, I have not checked.
So it varies from
It varies from each, what happens, total number of permutations are 8 factorial.
but different kind of combinations are not.
Right, because only 2 raised to power 12 possible combinations can be set, because you can either be in cross or bar state, there are total 12 switches, and this can take 2 states, so 2 raised to power 12 possible permutations can be set. 2 raised to power 12 is smaller than 8 factorial. Okay. So, 8 factorial minus 2 raised to power 12, those combinations are not permitted by a switch. 8 factorial is higher than 2 raised to power 12. I can prove that. I can prove that. So, this is 8 factorial, fine, 2 cube, थ्री 4 2 6 1 7 no, this 3 will also come, no? 2 into 3 6 has been broken. So, how much is this number? 21 पंजे 105 और 3
Sir, without calculating also from here I can get 2 to the power 7. 7 is greater than 2 square.
2 raised to power 2.
5 is greater than 2
2 raised to
square.
power 2.
yeah 7 2 to the power 7 2 to the power 5 2 to the power 5 is 32 and this number is greater than 32 actually. So, these mean this much is the difference which you will have in the permutations, but I am not interested in the permutation as of now. I am only interested in kind of what is the blocking probability, that is basically is the issue. Okay. So, now coming to the actual definition. Now, this is with 2 by 2 is all life is very simple. Want a simplified version? I think go with a Benz network. So, I think the most important thing which is there is you have figured out that how to connect to create a delta network. Make sure you always create a demultiplexer tree, and the inputs to a switch should always come from the same output number from the switches in earlier stage. There has to be exactly one connection from a switch in the previous stage to the switch in the next stage. Another important thing, none of the input and outputs will be left free in the intermediate stages. All outputs in the output stage will be the outputs, and all inputs in the input stage will be the inputs or to the switch matrix. Okay. So, another one 8 by 8, I think this I had done earlier, but let me do it again. Okay. So, I will give a general proof for a shuffle thing, a generalized shuffle I will be talking about, not for this one. This one is pretty simple. I can take 0 here, 1 here, this is 0, 1 0 1. So, remember this can only take input from 1, this can only take input from 0. So, that condition has to be satisfied. So, this one tree I can make another one. I am actually drawing shuffle net here. This is 0, so it can go here. This is 1, so this can go here. This is 0, so this can go here. There are two trees, no links are common between these two trees actually so far. Okay. There is no link which is common in these two trees, that is the beauty of shuffle net actually. Now onward we will get, in fact you can very easily convert it to a Bayes network if you are smart enough. So, I think you think about it and I will ask how that will be done. So, this is 0, this is 1, so this can go here and I create a tree here and this one can go here, created a multiplexer tree. Okay. This is also a delta network. And how to create convert it to inverse Bayes? I can visualize that from here. So, yeah, you move it here and you move this thing here, you get inverse Bayes. Okay, these are like strings, you just take this block, move it here, this one you move it here, it is inverse Bayes, nothing else. So, sometimes the things are equivalent, but they do not seem to be equivalent actually. This is equivalent to inverse Bayes. So, now let us go to generalized definition for what we call the delta network. So, how formally it will be defined. It is a subclass of delta network. This is not shuffling. I will define what the shuffle is actually. This is not shuffling, but it is a delta network.
The link between the first and the second stage is symmetrical to second and third stage.
Link between first and second stage is exactly same, ditto. There is no change. Ditto. This is a shuffle. No, this particular thing is shuffle. Shuffle is one particular example which can be repeated between multiple stages. You require log 2 n stages actually. So, this is 8, log 2 n is 3. Log 2 of 8 is 3 in this case, because we are using 2 by 2 switches. But this is not a general definition. General definition is I will use a switch which will be of A by B, okay, and the number of inputs to a switch will be A raised power n, number of outputs will be B raised power n. Generalized delta network. Okay. So, now let us go to this structure, because this is what I will be using for proving that shuffle net actually in general, a generalized shuffle net is a delta network. We have to formally prove it. So, actually it is not evident, here it is fine, for 2 by 2 it was very simple, but you cannot keep on drawing for a very large size dimensional switch. So, the switch structure will be something like this now. I am coming to that. So, this will be made using A by B cross bar switches. So, I have to write actually many statements, these are all form the part of the definition. So, delta network will be in general will be built by A by B switches. So, A by B is a cross bar switch technically, it is equivalent to that, it is a strictly non-blocking switch. Output ports are numbered as 0, 1, 2 and B minus 1. Okay. They total be output ports in every switch. So, input ports will be numbered as What I should write? A minus 1, perfect. So, any A raised power n by B raised power n switch will contain n stages. So, we were having 2 cube by 2 cube switch, 3 stages because of that, because it was built with 2 by 2 switches. So, it will have n stages such that unique path, that is a condition for Banyan network, of constant length I will just remove this. Exist from any input to any output. And none of the inputs of any A by B switch, or I call it crossbar, are unconnected. So, this actually implies that from one stage whatever is the number of outputs has to be equal to number of inputs to the next stage. Okay, this is obvious, and from here actually you can, and of course we also know that now you will have A raised power n sources, they will be mapped onto B raised power n destinations or the output ports, and the stages will be numbered from 1 to till n. Starting from source side. So, how many modules will be there in the first stage? Yes, perfect, because A inputs are there to each switch, total number of inputs is A raised power n, so A raised power n divided by A, so it gives A raised power n minus 1. And what is the number of outputs which are coming from first stage? Each switch is the output of B, this is the number of modules has to be A raised power n minus 1 into B. So, this should be equal to number of inputs to the second stage. So, how many number of modules in the second stage? You again divide by A, number of outputs coming out of second stage, and so on. So, once we understand this, so ith stage we will have A raised power n minus I these many number of modules. each module will be of size a by b. So, what is the total number of modules? I can do summing up of all this with index I. Total number of modules will be this, and I can now sum it up. This will give me and this of course obviously is when A is not equal to B, because when A is equal to B this actually becomes 0 by 0 form, and when of course A is equal to B, in that case this summation will be nothing but n minus 1 which will be nothing but this. Obviously the constant will come out. So, either these many modules will be there when size is equal or this. So, for our case when n was 3, A was 2, so it is 3 into which was 12 for 8 by 8 delta network. But in general for A by B, because 2 by 2 was simpler, in general for A by B this is what will be the expression. So, now let us look at the rule of how you are going to construct with A by B. 2 by 2 was fine. A by B also you will follow the same rule. You will every time will create a demultiplexer tree every time, and you will still follow the same rule. So, I can do it for a very small example of 3 by 2 or something, and then take care of that. So, I am going to take 4 square by 3 square switch. So, it will be built with 4 by 3 switching elements, and it will be having 2 stages. Okay. So, you can, if you want, you can create for anything, but just this is an example of the principle which are followed for building up the topology. So, I create and I require 4 raised power n minus 1, 4 actually modules of 4 by 3 in the first stage. Second stage I will be requiring 4 into 3 is 12, 12 divided by 4 I require 3 more modules obviously. Okay. So, let us look at the first input 0 1 2, obviously there has to be only 0 input should come, and anyway I am only creating a demultiplexer tree. I got the demultiplexer tree. Since there are only 2 stages, it is actually simpler here. Same is here, this 0 has to go here, this 1 has to go here, because all the inputs has to come from the same numbers. got it, is also a delta network, and the addresses which you will be keeping is output addresses will be decided by the number there. So, there are only 3 outputs, remember. So, I require a b-ary digit. If it was 0 and 1, a binary bit. Now, I require 0, 1, 2 can only be the number, and there are 2 stages. So, I can use an address like 0, 0, 0, 1, 0, 2, 1, 0, because then I cannot have more than 2. These will be the addresses. So, first one will be used for routing in the first stage, second one in the second stage, and you will reach to the destination. So, these will be the numbers like 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1 and 2, 2. So, you can build up any kind of complex thing with this kind of structure. Make sure you make a demultiplexer tree every time for every input which you are going to connect, while maintaining the same condition. And of course, there can be, in general, can be many possible ways you can create. So, now let us look at shuffle network, which is the one of the regular interconnection pattern which can be periodically put between all n stages. Okay. So, generalized shuffling we have to identify. So, Q shuffle of QR objects, how that will be defined? So, what shuffling is, technically I have got a stack, I build up another stack, I can build any number of stack. Shuffling means take first from here, second from here, first from here, second from here. I did the shuffling. So, usually when you are playing cards, you are always making 2 actually portions, and then you are taking one from here, one from here. That is how you do the 2 shuffle actually there. In general, there need not be 2 shuffle, there can be K shuffle. So, you can actually put all the cards into K separate packets, take one from here, one from each packet every time in round robin fashion, and you create a K shuffle in that case. So, we want to actually now give a generalized definition, because this is required for me for doing the address mapping, okay, because the proof is by induction. So, Q shuffle of QR objects will be defined as, this will be denoted by where Q and R are positive integers. This is nothing but I am generating a permutation of indices, QR indices, which are 0, 1, 2, QR minus 1. And this will be defined by S of QR Q into I. Okay, so I is the basically the input side. So, there is an interconnection pattern from input to output. So, you have numbers like this 0, 1, 2, 3 till QR minus 1. I am now trying to generate a map to this. So, this interconnection pattern is what is shuffle. So, for if you take this ith pattern which is sitting here, this I is mapped to what? That is what we are trying to figure out through a formula. So, it will be always Q into I, it is a Q shuffle. If there are 2 shuffle, I multiply by 2 and then do it actually. Okay, 2 shuffle means there are 2 cards. So, if I take the first one, the next one has to go to the, you have to leave something in between, that is why Q into I will be there. So, the 0 will be connected to 0, 1 will be connected to 2, not to 1, 2 will be connected to 4 and so on, but then the number will saturate, then you have to do a modulo operation. So, for this is actually for that.
So when I am taking Q into I, here I am assuming that Q shuffles of I are permitted.
Q shuffling, what I am implementing now of QR objects.
But if I have a stack of QR minus 1, the maximum possible shuffles.
QR minus 1 is not the stack, stack is of QR objects.
Okay, of QR objects.
They are numbered from 0 to QR minus 1. This 0 also you have to count, na? Actual number of objects is how much? 1, 2, 3 QR. They are numbered in this fashion. They are actually numbered in this fashion, because in computing we always start 0 is always included, always the first object. So, if you have n address line, they will be numbered always from 0, 1, 2, 3 till n minus 1.
That's fine. But still the number of shuffling can be greater than Q into I.
I am not able to understand.
This is for a particular
I, Q into I can be greater than QR.
yeah.
That is fine, there is a modulo operation. Okay, I am going to give an example with this. There are two expressions which actually can be used, one of them is this actually, and of course the equivalent expression which also can be used is this. See, these both are equivalent expressions. So, for the 8 by 8, let me build up a 2 shuffle with this. Okay. So, 1, 2, 3, 4, 5, 6, 7, 8, numbered from 0, 1, 2, 3, 4, 5, 6, 7. So, we will do with the first formula first. Okay. So, Q into R is 8. What is R? Is 4, Q is 2. So, I have correspondingly the numbers here 0, 1, 2, 3, 4, 5, 6, 7. Okay, let me just do it parallelly actually. Okay. So, I is 0, 0 into Q is 0, I divide by R, I have to find out an integer which is lower than I by R, highest integer which is lower than I by R actually, that is what it means, I by, that is the lower floor, that is the floor function, this which I have drawn. This actually means the integer which is lower, highest integer which is lower than I by R. Okay. There is similarly a ceiling function which is the lowest integer which is higher than the number. So, 0 into 2 is 0, 0 by R is 0. So, highest integer lower than or equal to 0 is 0 actually, and modulo QR it will get a 0, so 0 has to be connected to 0. When it is 1, 1 into Q, Q is 2 here, you will get 2, and 1 divided by R, R is 4 actually, remember. So, 1 by 4 is a number which is a fraction. So, integer highest integer lower than that is 0 actually. So, 1 into 2 will give me 2. What 2 will give? 2 into 2 is 4, 2 by 4 neglect the other part, that 4th thing. So, this will be connected to 4, 3 will be connected to 6. When the 4 will come, So, 4 into 2 is 8, okay, which is fine. 8 plus 4 by r is 4 by 4 is 1. So, that number will come out to be 1 when you take the floor function. 4 by 4 is 1, so that will be 1. So, 8 plus 1 is 9. 9 modulo of 8 is how much? So, I have 4 will be connected to 1. Try for the fifth similarly. So, 5 into 2 is 10, 10 plus 5 by 4 floor function will give you 1, okay. So, 10 plus 1 is 11, 11 modulo 8 is 3. Similarly for 6, this is what was exactly the shuffle net which I had drawn, but binary was easier to remember, but in general you can do for Q shuffling. Now use with the second formula, this will also give the same result actually, not an issue. So, 0 will give you 0, q into I modulo qr modulo 7 now, okay. 1 will give you 2, 2 will give you 4, 3 into 2 will give you 6, 6 is actually modulo because 7 I am taking, 4 will give you 4 into 2 is 8, modulo 7 will give you 1, right connection. 5 into 2 is 10, modulo 7 will give you 3, 6 into 2 is 12, modulo 7 will give you 5, which is perfect, and when qr I is equal to qr minus 1, that time you have to use this I, the lower part, it also gives. So, that is a basically thing which we will be using now for doing transformation of address lines actually ultimately.
Sir, what is the advantage of having this shuffle networks? Why are they useful?
Shuffle will give you the same connection pattern between multiple stages. So, while you are implementing in silicon, the same mask can be simply repeated 3 times, or it is a larger switch, same thing you repeat multiple times. If you do not do that, your cost of fabrication actually will go up. You require n different kind of interconnection and different kind of masks. You cannot simply repeat. Well, that is I think is the issue. If it is an optical thing and I am making a kind of a planar array of transmitter, then I put another one on top of it. So, I require some between holographic interconnect. Every time you have to design a different holographic interconnect between stages. If the same thing is repeated, you only make it once, make multiple copies, push it. Mass production reduces the cost. Yeah, that is all. That is all optical implementations will be something like this. You will have transmitters here. Each one is a processor, it will connect 2 inputs. On top of this, you will actually have a slab, which is a holographic thing. Computational holography actually is used. You create phase grating technically, but depending on what interconnection pattern is required. But remember, it is a 2-dimensional thing, it is not 1-dimensional. Here I am actually drawing 1-dimensional. So, 2-dimensional also can be done in the same fashion, but I am not moving to 2-dimensional thing here. But that is actually a altogether a different domain. That is, I think some other course probably this can be discussed, but we do not have a course on optical computing, so you do not get opportunity. Any course on optical computing will talk about this, the structures. So, maybe some other semester I will try. So, I think we will close here. So, shuffle now we have understood. I will take exactly this thing and we will start a formal proof that shuffle net actually is a delta network, a generalized shuffle net, which will follow this interconnection pattern from the output of ith stage to I plus first stage. Mapping is done as per this.